Picture this. You're walking through an ancient forest, the kind where moss hangs from branches like nature's curtains and the air smells of earth and time. Then you see it, a massive oak tree, not just big, impossibly big. Its trunk is wider than a house, its branches reach up so high they disappear into the clouds, and the bark looks like it's been weathered by centuries of storms. You'd swear this tree has been standing here for at least 500 years. But then you look down at the soil around it, and your brain just stops. Because the ground beneath this ancient giant only formed yesterday. The dirt is fresh, you can still see where it was dumped. That tree shouldn't be there. It can't be there. The math doesn't work, the biology doesn't work, nothing about this makes sense. You'd probably think you were losing your mind, right? You'd blink hard, rub your eyes, maybe even pinch yourself to make sure you weren't dreaming. Well, I want you to hold on to that feeling of impossible wrongness, because that exact sensation, that gut-level, this can't be real confusion, is what the smartest scientists on Earth are experiencing right now. They're staring into the deepest, darkest corners of space, looking back to the very dawn of time itself, and they're finding cosmic monsters that have absolutely no business existing. We're talking about supermassive black holes. Not the little ones that form when a single star dies. No, we're talking about things so unfathomably heavy that they contain the mass of billions of suns, compressed into regions smaller than our solar system. Objects so dense that they literally tear holes in the fabric of space and time. And here's the problem that's keeping astrophysicists awake at night, staring at their data with a mixture of excitement and existential dread. We're finding these billion-sun monsters in the very first moments of the universe's existence. It's like finding a fully grown adult human in a world that's only been around for a week. Not a baby, not a toddler, a full-grown, 6-foot-tall adult. This isn't just a small error in our calculations. This isn't something we can fix by tweaking a few numbers in our equations. This is a fundamental, everything we thought we knew might be wrong kind of problem. This is the universe looking us dead in the eye and saying, yeah, all those textbooks you wrote, all those theories you spent decades building, they're cute, but they're wrong. And I'm not exaggerating when I say this might be the single biggest dilemma in the history of space science. Because if we can't figure out how these monsters got there, then we don't understand how galaxies formed. And if we don't understand that, then we don't really understand how we got here. Before we dive deeper into this cosmic detective story, I need to tell you about a moment that changed how I think about all of this. A few years ago, I was giving a talk at a university about black holes, and a student raised their hand and asked me, "Do you ever feel scared when you think about what we don't know?" And honestly, I lied. I said no. I gave some confident answer about how exciting mysteries are. But the truth is, yes, sometimes I do feel scared. Not in a horror movie way, but in a deeply humbling way. Because we're floating on a tiny rock in a universe that's 13.8 billion years old. And we're just now, just in the last few years, discovering that our entire understanding of how that universe grew up might be fundamentally broken. That's terrifying, but it's also the most thrilling thing I can imagine. So today, we're going on a journey together. We're going to unpack this mystery step by step. We're going to look at what black holes actually are, why they shouldn't be able to grow as fast as we're seeing them grow, and what radical new theories scientists are proposing to explain these impossible giants. Fair warning, by the end of this, your brain might hurt a little. Some of what we're going to talk about sounds like science fiction, but I promise you, every single thing I'm about to share is backed by real data from real telescopes looking at real objects in space. This isn't speculation. This is the cutting edge of our understanding of reality itself. And before we move forward, I want to plant a question in your mind, one that we won't answer until much later. If these monsters were born at the dawn of time, and if they helped build the galaxies around them, does that mean we owe our entire existence to them? Are we in some weird cosmic sense the children of black holes? Hold on to that thought. We'll come back to it. But first, we need to start with the basics, because to understand why these early monsters are so impossible, you need to understand what a black hole actually is and how we thought they were supposed to grow. Okay, Let's strip away all the complicated physics for a minute and talk about black holes in the simplest terms possible. Forget everything you've seen in movies where they're portrayed as cosmic vacuum cleaners sucking up entire spaceships. Let me give you a better way to think about them. Black holes are what happen when gravity wins the ultimate, no-holds-barred championship fight against every other force in the universe. In our everyday lives, gravity is actually pretty weak. You might not think of it that way, but consider this. You can jump. Right now, you could stand up and jump, and for a brief, glorious moment, you would beat the combined gravitational pull of the entire Earth, all 6 billion trillion tons of our planet pulling down on you, and your legs can overcome it. That's how weak gravity is on human scales. But here's the thing about gravity. It never gives up. It never gets tired. And most importantly, the more mass you pack into a small space, the stronger it gets. Exponentially stronger. So imagine this thought experiment with me. Take the Earth, our entire planet, with all its mountains, oceans, cities, and that weird layer of molten rock in the middle. Now imagine crushing it. Keep crushing it, smaller and smaller. Through some impossible cosmic press, you squeeze our entire planet until it fits in the palm of your hand. If you could actually do that, and to be clear, nothing in our technology could come even remotely close to doing this, the gravity would become so insanely strong that not even light could escape. And light is the fastest thing in the universe. Nothing can go faster than light. It's the universal speed limit. But in that crushed Earth in your palm, gravity would be so powerful that even photons of light trying to escape would be pulled back down. That's a black hole. It's not a thing. It's not an object made of matter in any conventional sense. It's a point where space and time themselves basically give up and say, we can't handle this anymore. The math breaks, the physics breaks, everything we understand about how reality works just stops. Now, I know what some of you might be thinking. Okay, but black holes are rare, right? They're these weird edge case things that only happen in extreme circumstances. And that's what we thought for a long time too. We figured black holes were these scary but uncommon objects, maybe one every few galaxies, formed when the biggest stars died in spectacular explosions. But then we started looking more carefully at galaxies, and we discovered something that fundamentally changed astronomy. Almost every single galaxy we can see, every single one, has a supermassive black hole lurking right in the center of it. Our own galaxy, the Milky Way, has one. We call it Sagittarius A star, pronounced Sagittarius A star because astronomers are terrible at naming things. It sits right in the galactic center, about 26,000 light-years away from us, and it's heavy, really heavy, about 4 million times more massive than our Sun. Let me help you visualize that for a second. Our Sun is already unbelievably massive. It makes up 99.8% of all the mass in our entire solar system. All the planets, all the asteroids, all the comets, all the gas and dust combined barely register compared to the Sun. And Sagittarius A star is 4 million times heavier than that. If you could somehow swap our Sun out and replace it with Sagittarius A star, it would swallow everything. Mercury, Venus, Earth, Mars, all of them would be inside the event horizon, gone. The black hole would extend out past the orbit of Earth and keep going. It would be the ultimate cosmic game over. But here's what's wild. Even our galactic black hole, this 4 million solar mass monster, is a complete lightweight in the grand scheme of things. There are black holes out there that make Sagittarius A star look like a grain of sand. One of them sits in a galaxy called Holmberg 15A, and it weighs in at approximately 40 billion solar masses. 40 billion suns. I need you to really sit with that number for a second, because it's almost impossible to comprehend. If our Sun is a grain of sand, this thing would be the size of a massive skyscraper. If you wanted to count to 40 billion, counting one number per second without stopping for food or sleep, it would take you over 1,200 years. And that black hole isn't even the biggest one we know about. There are a few others that might be even more massive. So how do things like this form? How does something become so preposterously heavy? For decades, we had a nice, neat story that made perfect sense. It went like this. A long time ago, not in a galaxy far, far away, but right here in our own universe, a massive star died. Not a normal star like our Sun. We're talking about the first generation of stars, the population 3 stars, which were hundreds of times more massive than the Sun. When one of these monsters ran out of fuel, it collapsed and exploded in what we call a supernova. But the core? The core collapsed down into a black hole. That first black hole would have been relatively small, maybe 10 times the mass of the Sun, maybe 100 times at most. A baby black hole by cosmic standards. Then, over billions of years, that baby would grow up. It would sit in the center of its galaxy, slowly eating any gas or dust that wandered too close. And whenever its galaxy collided with another galaxy, which happens surprisingly often in the early universe, the two black holes would eventually find each other, dance around in a death spiral, and merge into one bigger black hole. Little by little, collision by collision, bite by bite, these black holes would grow. After billions of years of this slow, patient growth, you'd eventually end up with the supermassive monsters we see today. This story was beautiful. It was logical. It was like watching a business grow from a single dollar into a billion-dollar empire through hard work, smart investments, and compound interest over many years. Slow and steady wins the race, right? This theory worked perfectly to explain the black holes we see in the nearby modern universe, the ones that have had billions and billions of years to grow. But then, we got a new set of eyes. We got the James Webb Space Telescope. And everything fell apart. James Webb isn't just an upgrade from the Hubble Space Telescope, it's a completely different beast. Hubble mostly sees visible light, the same kind of light your eyes see. But there's a problem with that when you're trying to look back to the beginning of the universe. As the universe expands, it stretches the light traveling through it. It's like if you drew a wave on a rubber band and then stretched the rubber band, the wave gets longer, stretched out. Light from distant galaxies gets stretched so much that by the time it reaches us, it's no longer visible light. It's been shifted into the infrared spectrum, which is invisible to our eyes and to Hubble. James Webb was specifically designed to see in infrared. It's like putting on night vision goggles that let us see things that were previously hidden in the dark. When we turned Webb on and pointed it at the deepest, most distant parts of the universe, we expected to see those Lego bricks I mentioned. Tiny, faint baby galaxies just starting to form, with maybe the tiniest hints of small black holes beginning to grow. That's not what we found. Instead, Webb looked back to when the universe was only about 500 million years old, which sounds like a long time, but remember the universe is 13.8 billion years old, so we're talking about less than 4% of the universe's total age. And it saw galaxies that were already massive. And inside those galaxies, black holes that were already hundreds of millions or even billions times the mass of the Sun. Let me repeat that because it's so important. We found black holes with the mass of 1 billion suns in a universe that was only 500 million years old. This is where our nice, neat story completely collapses like a house of cards in a windstorm. If you start with a seed black hole that's, say, 100 solar masses, which is generous for a stellar black hole, and you give it 500 million years to grow, and you let it eat at the absolute maximum rate that the laws of physics allow, eating constantly every single second without ever taking a break, it still wouldn't even come close to 1 billion solar masses. It's not even in the same ballpark. It's like asking someone to run a marathon in 5 minutes. Even the world's fastest human being, going at their absolute top speed without stopping, couldn't come anywhere near doing that. The physics just doesn't allow it. So we're left with a mystery that feels almost like a crime scene. We have a victim, our old theory of slow black hole growth. We have evidence that the theory is wrong, these impossible monsters in the early universe. And we have to figure out, how did they do it? How did they get so big so fast? Did they find a way to cheat the laws of physics and eat faster than should be possible? Or, and this is where things get really interesting, did they not start small at all? What if these black holes were born massive? What if they skipped the whole baby phase entirely and came into existence already weighing millions or billions of suns? And here's something I haven't told you yet, something that makes this even more mind-bending. We're not just finding 1 or 2 of these early monsters, we're finding them everywhere we look. It's not a fluke. It's not bad data. The more we search, the more we find. These things are common in the early universe, which means whatever process created them wasn't some ultra-rare cosmic accident. It was somehow a normal part of how the universe developed. Before we go further, I want you to think about this. Every atom in your body was forged in the heart of a star or in the explosion of a supernova. You are quite literally made of stardust. But what if the process that allowed those stars to form in the first place was orchestrated by black holes that shouldn't exist? What if the entire story of the universe, including the story of how we came to be, hinges on understanding these impossible monsters? In our next part, we're going to dive deeper into that old story I mentioned. We're going to look at the Lego brick method of building the universe and see exactly where and why the bricks started falling apart. We're also going to examine James Webb more closely and understand how this telescope is basically acting like prescription glasses for a humanity that's been squinting at the dark for our entire existence. But I'll give you a preview of where this is heading. The evidence is so overwhelming at this point that scientists are starting to consider ideas that sound like they came straight out of science fiction. Ideas about black holes that formed in the first millisecond of the Big Bang. Ideas about gas clouds collapsing so fast and so violently that they never had a chance to form stars. Ideas that challenge everything we thought we knew about gravity, time, and the very structure of reality. The universe has secrets, big ones, and we're just starting to pry them open. Before we can fully appreciate how revolutionary and world-shaking these new discoveries are, we need to understand what we believed for so long and why it seemed so reasonable at the time. Because here's the thing, the old theory wasn't stupid, it wasn't lazy thinking, it was actually brilliant, backed by solid math and observations, and it explained almost everything we could see with our telescopes. Until it didn't. I like to call the old model the Lego brick method of universe building. The core idea was simple and elegant. The universe started out simple and built itself up one small piece at a time, gradually and methodically over billions of years. It was a story of patience, of compound growth, of slow but steady progress. Here's how the story went. In the very beginning, right after the Big Bang, the universe was filled with almost nothing but hydrogen and helium. These are the simplest elements, just protons and electrons in the case of hydrogen, and slightly more complex but still simple for helium. No carbon, no oxygen, no iron, none of the elements that make up planets and life, just the most basic building blocks. As the universe expanded and cooled, gravity started to work its magic. In some places, the gas was slightly denser than in others, just random fluctuations, tiny variations in density. But gravity loves density. Where there's more mass, gravity pulls harder, which attracts even more mass, which makes gravity pull even harder. It's a runaway effect. Eventually, these dense regions pulled in enough gas that they started to collapse. And when gas collapses and gets squeezed, it heats up. Squeeze it enough, and it gets hot enough for nuclear fusion to ignite. Suddenly, you have a star. But these weren't stars like our sun. These were the first stars, what astronomers call population 3 stars, and they were absolute monsters. Because they were made of pure hydrogen and helium with no heavier elements mixed in, they could grow to be absolutely massive, hundreds of times heavier than the sun. They were the heavyweight champions of the early universe. The problem with being that massive is that you burn through your fuel incredibly quickly. These stars lived fast and died young. While our sun will burn steadily for about 10 billion years, a population 3 star would exhaust its fuel in just a few million years. And when they died spectacularly, in explosions so violent that they temporarily outshone entire galaxies. These explosions, supernovae, created the first heavier elements. All that nuclear fusion in the star's core had been building carbon, oxygen, nitrogen, iron, and all the other elements on the periodic table. The explosions scattered these elements out into space, enriching the gas clouds that would form the next generation of stars. Each generation would be slightly more metal-rich. In astronomy, anything heavier than helium is called a metal, which drives chemists crazy, but that's the terminology we use. And when these massive stars died, their cores would collapse. If the star was big enough, that collapse would create a black hole. This would be the seed, a baby black hole weighing maybe 10 to 100 times the mass of the Sun. Now, according to the old story, this baby black hole would spend the next billions of years growing. It would grow in two main ways. First, it would eat. Black holes don't exactly eat in the way we think of eating, but it's a useful metaphor. Any gas or dust that drifted too close would get pulled into orbit around the black hole, forming what we call an accretion disk. Over time, friction would cause material in that disk to gradually spiral inward, eventually crossing the point of no return and falling into the black hole. Mass goes in, the black hole gets heavier. Simple. Second, black holes would merge. The early universe was a crowded, chaotic place. Galaxies were constantly smashing into each other. When two galaxies merged, their central black holes would eventually find each other through the chaos. They'd spiral around each other in a gravitational dance that could last for millions of years, radiating energy in the form of gravitational waves, until finally they collided and merged into one bigger black hole. Bit by bit, meal by meal, merger by merger, these black holes would grow. It was like compound interest in a savings account. Start with $1, add a little bit each year, wait a really long time, and eventually you have a fortune. This model was tested and refined for decades. We could see black holes in nearby galaxies that fit the pattern perfectly. We could measure their masses, look at the ages of their host galaxies, and the numbers worked. A 13.8 billion-year-old universe? Plenty of time for a baby black hole to grow into a billion solar mass giant through this slow, steady process. Everything made sense. The textbooks were written. The Nobel Prizes were awarded. We thought we had it figured out. And then we built James Webb. James Webb Space Telescope is, without exaggeration, one of the most remarkable machines humanity has ever constructed. It's worth taking a moment to appreciate what an absolute miracle of engineering it is, because understanding what Webb can do helps us understand why its discoveries are so earth-shaking. Webb's primary mirror is over 21 feet across, huge by space telescope standards, and it's made of 21 hexagonal segments, each plated with a microscopically thin layer of gold. Why gold? Because gold is the best reflector of infrared light, and infrared is what Webb was designed to see. The telescope sits not in orbit around Earth like Hubble, but at a point in space called L2, about 1 million miles away from Earth in the opposite direction from the Sun. It sits there in the shadow of our planet, protected from the Sun's heat by a tennis court-sized sun shield made of 5 layers of incredibly thin material. This keeps Webb's instruments at around -370 degrees Fahrenheit, which is crucial because infrared detectors need to be extremely cold to work properly. When you point Webb at a distant part of the sky and let it stare for hours, gathering every photon it can, something magical happens. Light that has been traveling through space for billions of years, light that left its source when the universe was a baby, finally arrives at Webb's mirror. That light has been stretched and redshifted by the expansion of the universe, but Webb can see it. Webb can capture it and turn it into an image. Essentially, James Webb is a time machine. When we look at an object that's 13 billion light-years away, we're not seeing it as it is today. We're seeing it as it was 13 billion years ago, because that's how long it took the light to reach us. We are literally looking back in time.
When scientists first pointed Webb at the very edge of the observable universe, at regions of space so distant that we're seeing them as they were in the first few 100 million years after the Big Bang, they had very specific expectations. They expected to see the universe in its infancy, small, primitive galaxies just starting to form, tiny black holes just beginning their long journey of growth. They expected to see those Lego bricks being placed one by one. That's not what they saw. What they saw were galaxies that looked surprisingly mature, Galaxies with structure, with organized spiral arms, with massive amounts of stars already formed. And in the centers of these galaxies, they saw something that made them question everything: supermassive black holes. Not baby black holes, not black holes in the process of slowly growing, but black holes that were already hundreds of millions or billions times more massive than the Sun. One of the most dramatic examples came from a galaxy called GNZ11. This galaxy is so far away that we're seeing it as it was just 400 million years after the Big Bang. The universe at that point was only about 3% of its current age. It would be like looking at a human baby who was only 3 weeks old. And yet, sitting in the center of this infant galaxy, they found a black hole that was already more than 1,000,000 times the mass of the Sun, possibly even more massive than that. The exact measurements are tricky at these distances, but the numbers are in that ballpark. Let me explain why this is so shocking. If you start with a seed black hole of, say, 100 solar masses, which is already quite generous for a stellar black hole, and you let it eat at the maximum possible rate allowed by physics, it would take about 30 to 40 million years just to double its mass. To go from 100 solar masses to 1,000,000 solar masses, you'd need to double roughly 13 times, because 2 to the 13 is about 8,000, and we need to get to 10,000 to go from 100 to 1,000,000, so a few more doublings beyond that. Even if we're generous and say each doubling takes only 30 million years, that's still around 400 to 500 million years minimum. That means this black hole would have had to start eating at the absolute maximum rate from the moment the universe began, with no breaks, no pauses, no periods of inactivity, to even barely reach the mass we observe. There's essentially zero margin for error. And that's assuming perfect conditions. In reality, black holes don't eat constantly. They go through active periods and quiet periods. The gas supply isn't infinite. Sometimes the radiation pressure from all that infalling material actually pushes new material away, creating natural breaks in feeding. But it gets worse. GNZ11 isn't a unique case. It's not an outlier. As Webb has continued its observations, we've found more and more of these impossibly early, impossibly massive black holes. They're not rare. They're not flukes. They appear to be common in the early universe. Astronomers started finding what they call little red dots. At first, these just looked like tiny points of reddish light in Webb's images, but when they analyzed the spectrum of that light, essentially breaking it down to see what elements and processes were producing it, they realized they were looking at incredibly massive black holes actively feeding. These weren't quiet black holes sitting dormant. They were active, voracious, growing at rates that shouldn't be physically possible. And they were everywhere. One particularly striking discovery involved a galaxy called UHZ1. This galaxy is so far away that we're seeing it as it was just 470 million years after the Big Bang. And the black hole in the center of this galaxy? It weighs about as much as all the stars in the rest of the galaxy combined. Think about that for a second. In a normal galaxy like our Milky Way, the central black hole represents about 0.1 to 0.2% of the total mass of the galaxy. It's a tiny fraction. The galaxy is the main event, and the black hole is just a small, albeit important component in the middle. But in UHZ1, the black hole is half the show. It's like if your heart weighed as much as the rest of your entire body. The proportions are completely out of whack. Scientists call these overmassive black holes, and they're finding them throughout the early universe. This was the moment when the old Lego brick theory definitively died. There was simply no way to fit these observations into the old model. You cannot build a billion solar mass black hole in 500 million years starting from a stellar seed, no matter how generous you are with your assumptions. The math doesn't work. The physics doesn't work. Something else must be going on. I remember when these first results started being published in academic journals. I was at a conference, and I watched a room full of the world's top astrophysicists stare at the slides with expressions that ranged from confusion to disbelief to barely contained excitement. Because when your theory breaks, when the universe shows you that you were wrong, that's not a failure. That's an opportunity. That's the moment when you're on the verge of discovering something completely new about how reality works. But before we get into the radical new theories being proposed to solve this mystery, we need to understand one more crucial piece of the puzzle: the speed limit. We need to talk about why it's so hard for a black hole to grow and what physical laws put the brakes on their feeding. Because if we're going to propose that these early black holes somehow grew faster, we need to understand exactly what they'd be up against. In the next part, we're going to dive deep into the physics of hunger. We're going to talk about the Eddington limit, the cosmic speed bump that prevents black holes from growing too quickly. And we're going to see just how enormous the challenge is for any theory that tries to explain these early monsters. But here's a teaser for you. What if the answer isn't that they grew faster? What if the answer is that they never started small at all? What if somehow the universe found a way to create massive black holes right from the start, skipping the baby phase entirely? And if that's true, how did it do it? Hold that question. We're about to find out.
Now we get to the physics. Don't worry, I promise to keep this accessible, but this part is crucial because it shows us exactly why the early universe black holes are such a problem. To understand that, we need to understand the Eddington limit, which is basically the cosmic speed limit for how fast a black hole can grow. You'd think that a black hole with its supposedly infinite gravity, that's not actually true, but it's a common misconception, could just gobble up whatever it wants as fast as it wants, just open wide and swallow everything in sight. But the universe doesn't work that way. There's a delicate balance at play, and that balance puts hard limits on growth. Let me give you an analogy that helped me understand this when I was first learning about it. Imagine you're at an all-you-can-eat buffet. You're hungry. You want to eat as much as possible, as quickly as possible. But every time you try to take a bite, someone points a leaf blower directly at your face and turns it on full blast. The harder you try to shove food in your mouth, the stronger the wind becomes, until eventually your food is just flying across the room and you can't get a single bite. That's essentially what happens to a black hole trying to eat. Here's what's going on. When a black hole starts pulling in gas, that gas doesn't just fall straight in like water going down a drain. Due to conservation of angular momentum, basically things want to keep spinning if they're already spinning, the gas forms a disk around the black hole. This is called an accretion disk. Now, as that gas spirals inward, getting closer and closer to the black hole, something important happens. It gets squeezed. Particles rub against each other. Friction creates heat. And we're not talking about warm heat, we're talking about millions of degrees. The gas gets so hot that it starts glowing with an incredible amount of energy. This is where things get interesting. That glowing hot gas produces light, lots of it. In fact, an actively feeding black hole can produce more light than an entire galaxy's worth of stars. These are the brightest continuous light sources in the universe. Now, here's the critical part that most people don't realize. Light has pressure. Photons, particles of light, actually push against things. In our everyday life, this pressure is so tiny that you'd never notice it. If you shine a flashlight at your hand, you don't feel the light pushing back. But near a black hole, where the light output is absolutely enormous, that pressure becomes significant. It's like the difference between a gentle breeze and a hurricane. The radiation pressure from all that light literally pushes back against the inflowing gas, trying to blow it away. This creates a cosmic tug of war. Gravity is pulling the gas inward, trying to make the black hole grow, but the light created by that very process is pushing the gas outward, trying to prevent more from falling in. There's a critical balance point where these two forces are exactly equal. Below that point, gravity wins and the black hole can keep eating. Above that point, the radiation pressure wins and the gas gets blown away before it can fall in. This balance point is called the Eddington limit, named after Arthur Eddington, the brilliant astrophysicist who first figured this out in the 1920s. The Eddington limit puts a hard cap on how fast a black hole can grow. If a black hole is eating at its Eddington limit, the maximum possible rate, it takes about 30 to 45 million years to double its mass. That might sound fast, but remember, we're trying to go from 100 solar masses to 1 billion solar masses. That's not doubling a few times. That's doubling roughly 23 times, since 2 to the 23rd is about 8 million, close to the 10 million factor we need. Even at the absolute maximum eating speed, never stopping, never taking a break, it would take somewhere between 700 million and 1 billion years to reach a billion solar masses starting from a 100 solar mass seed. But we're finding black holes that massive at 400 to 500 million years after the Big Bang. The math literally does not work. The universe is showing us something that our physics says should be impossible. Now, some scientists have proposed what's called super-Eddington accretion as a possible solution. This is the idea that maybe, under very specific circumstances, a black hole could find a way to eat faster than the Eddington limit normally allows. Think of it like this. Imagine that buffet leaf blower again, but instead of the wind hitting you from all directions, you could somehow channel it, direct it to blow just in two narrow jets straight up and straight down, while leaving a clear path for food to come in from the sides. You'd still be producing the same amount of wind, but you'd have found a loophole that lets you eat faster. This is actually something we observe in real black holes. Many active black holes produce enormous jets, streams of energy and particles that shoot out from their poles at nearly the speed of light, extending for millions of light years. These jets seem to be the result of twisted magnetic fields channeling some of that radiation and energy away from the accretion disk. If most of the light could be directed into these jets instead of pushing back on the inflowing gas, then theoretically, a black hole could eat faster than the Eddington limit normally allows, maybe even 5 or 10 times faster in the most extreme cases. But even if we're incredibly generous and assume these early black holes were eating at 10 times the Eddington limit continuously for their entire lives, which would require perfect conditions that we have no evidence actually existed, the timeline is still extremely tight. You'd need everything to go right all the time with no breaks for hundreds of millions of years. It's possible technically, but it requires threading an extremely narrow needle. And this brings us back to the light seed problem that I mentioned earlier. If the first black holes came from the first stars, those population 3 stars we talked about, they were starting out with a huge disadvantage. They were starting poor, with only a few hundred solar masses at most. To reach a billion, they had to grow by a factor of about 10 million. That's a massive amount of growth, and it had to happen in a cosmologically short amount of time. It's like being told you need to turn $100 into $1 billion in less than 5 years. Sure, it's technically possible if literally everything goes perfectly and you make nothing but brilliant decisions and get incredibly lucky, but let's be honest, it's not happening. So scientists started asking a different question. What if the seeds weren't light at all? What if they were heavy from the start? This is where things get really interesting. Instead of starting with a black hole that weighed 100 suns, what if some black holes started their lives already weighing 100,000 suns, or even 1,000,000 suns? If you're trying to save $1 billion, starting with $100,000 instead of $100 changes the entire game. You don't need nearly as many doublings. The timeline becomes much more reasonable. But here's the problem. Making a heavy seed black hole is really, really hard. You can't just wish 100,000 solar masses worth of matter into a black hole. You need a mechanism. You need a process that can take a massive amount of gas, enough to make 100,000 stars, and collapse it all at once into a black hole without letting it fragment into stars first. And that's the challenge that scientists are grappling with right now. Because in normal circumstances, when a big cloud of gas collapses, it doesn't stay together. It fragments. It breaks apart into smaller clumps, each of which becomes a star. By the time you're done, you don't have one massive black hole, you have a star cluster with thousands or millions of individual stars. It's like trying to drop a big ball of dough onto the ground and have it stay as one solid ball instead of splattering into 100 pieces. The physics naturally wants it to splatter. You need special conditions to keep it together. So how do you create those special conditions? How do you make a heavy seed black hole? That's the question that's driving some of the most exciting research in astrophysics right now. And scientists have come up with some radical ideas that sound like science fiction but are backed by serious math and increasingly by observations from James Webb. But before we get into those ideas, I want to share something that's been on my mind throughout all of this research. We spend so much time talking about black holes as these destructive, terrifying objects, And don't get me wrong, they absolutely are if you get too close. But there's something almost beautiful about the problem they're presenting us with. The universe is basically handing us a puzzle and saying, figure this out. You thought you understood how things work. You don't. Here's your chance to learn something new. I find that humbling in the best possible way. It reminds me that for all our technology and intelligence, we're still students. The universe is the teacher, and it's a patient teacher, but it doesn't give us the answers. It gives us the clues and makes us work for it. In the next part, we're going to explore the heavy seed theories in detail. We're going to talk about direct collapse black holes that form without ever being stars first. And we're going to look at one of the most exciting recent discoveries, a galaxy called the Infinity Galaxy, where James Webb might have actually caught a heavy seed black hole in the act of being born. But here's something to think about. If heavy seeds are the answer, if massive black holes can form directly from collapsing gas clouds, that raises another huge question. Why don't we see this happening in the universe today? Why was the early universe able to do something that the modern universe can't seem to do? What was different back then? Hold that thought. We're about to find out.
If the Lego brick method is too slow, and if supereating at the Eddington limit still barely solves the timeline problem, then we're left with one radical possibility. What if black holes didn't start small? What if some black holes were just born massive? This is the heavy seed theory, and it's one of the most exciting ideas in modern astrophysics. The core concept is simple but profound. Instead of a star dying and leaving behind a baby black hole that has to grow, a massive cloud of gas, big enough to make 100,000 or even 1,000,000 stars, collapses directly into a black hole all at once. No star phase, no supernova, just gas turning straight into a black hole. We call this direct collapse, and if it happens, it completely solves our timing problem. If you start with a black hole that's already 1,000,000 solar masses, you don't need much time at all to reach 1,000,000,000. You're already most of the way there. It's like starting a marathon at the 20-mile marker. Of course, you're going to finish faster than someone who started at the beginning. But as I mentioned in the last part, creating these conditions is incredibly difficult. Let me explain exactly why, because it gets at something fundamental about how gas behaves in space. When you have a big cloud of gas floating in space, gravity is always trying to make it collapse. More mass in one spot means more gravity, which pulls in more mass, which increases gravity further. It's a runaway process that should, in theory, create bigger and bigger objects. But there's a problem: heat. When gas is hot, the particles are moving fast, bouncing around, creating pressure that pushes outward. This pressure fights against gravity. So for a cloud to collapse, it needs to cool down. The particles need to slow down and lose energy. In the modern universe, this cooling is easy because the gas contains molecules like molecular hydrogen, H2, carbon monoxide, CO, and water vapor, H2O. These molecules are really good at radiating away energy. They absorb heat and then emit it as light, which carries the energy away into space. The cloud cools, pressure drops, and gravity wins. The cloud collapses and fragments into stars. That fragmentation is the key problem. As the cloud collapses, it doesn't stay as one uniform blob. It develops denser regions, and those regions collapse faster, and eventually you get thousands or millions of separate collapsing regions, each forming its own star. It's like when you drop a water balloon. It doesn't stay as one big ball of water, it splashes into 1,000,000 tiny droplets. To form a direct collapse black hole, you need to prevent that fragmentation. You need the entire cloud to collapse as one unified mass. And to do that, you need to keep the gas hot enough that it doesn't form molecules, so it can't cool efficiently, so pressure stays high, but not high enough to stop collapse entirely. It's a very narrow window of conditions. Scientists think this might happen in a scenario like this. Imagine a massive cloud of gas in the early universe. But nearby, there's a very bright and active galaxy, maybe one that already has a small quasar or a very actively feeding black hole. That galaxy is blasting out intense ultraviolet radiation. When that UV radiation hits the gas cloud, it breaks apart any molecules that try to form. It sanitizes the cloud, keeping it as pure atomic hydrogen and helium.
These atoms can't radiate heat away as efficiently as molecules can, so the cloud stays hot. But the cloud is also very massive, so gravity is still strong. Eventually, gravity overcomes the pressure, and the entire cloud collapses, all at once, as a single object. In a cosmic instant, which might still take thousands or millions of years, but that's fast in astronomy terms, you go from a cloud of gas directly to a supermassive black hole. No star, no supernova, just cloud to black hole. For a long time, this was a neat idea on paper, backed by computer simulations, but we didn't have direct evidence that it actually happened. It was theoretically possible, but was it real? And then James Webb found the Infinity Galaxy. The Infinity Galaxy, officially designated something much more boring, but Infinity Galaxy is the nickname that stuck, is one of the most remarkable objects Webb has discovered. It looks like a glowing figure 8, an infinity symbol in space. And when astronomers analyzed it, they realized what they were looking at. Two disc-shaped galaxies in the process of smashing into each other head-on. Galaxy collisions are fairly common, but this one was special because of its geometry. The two galaxies hit each other almost perfectly flat on, like two frisbees smacking together. This created an enormous shock wave in the gas between them, compressing it, heating it, and creating perfect conditions for direct collapse. And right in the middle of that figure 8, right in the bridge of shocked gas connecting the two galaxies, Webb found a supermassive black hole, not tucked away in the core of one of the galaxies, not orbiting off to the side, right in the middle, in the newest, most shocked material. This black hole weighs about 1 million solar masses, and critically, it's located in a region where there wasn't a galaxy before. It's not an old black hole that wandered over. It appears to have formed right there, from the collision. This might be direct evidence of a direct collapse black hole forming in real time. Well, real time in the sense that we're watching it happen billions of years ago since the light took that long to reach us, but you get the idea. The Infinity Galaxy isn't alone. Another galaxy called UHZ-1, which I mentioned earlier, shows similar signs. In UHZ-1, the black hole is so massive compared to its galaxy, roughly equal in mass to all the stars combined, that it's hard to explain unless the black hole formed first or formed independently. In normal galaxies, the black hole grows alongside the galaxy in what we call co-evolution. They influence each other. The black hole feeds, produces energy, which regulates star formation in the galaxy, which affects how much gas is available to feed the black hole, and so on. It's a feedback loop. But in these early overmassive black hole galaxies, the proportions are so far off from the usual relationship that it suggests something different happened. The black hole came first, or at least grew much faster initially, and the galaxy formed around it. Think about what this means for our cosmic story. For decades, we thought galaxies were the main characters, and black holes were just important supporting actors. But now it looks like in the early universe at least, the black holes might have been the leads. They were the first major structures to form, and they used their immense gravity to pull in gas, which cooled and formed stars, which became galaxies. The black holes were the architects, and galaxies were the buildings they constructed around themselves. This is a fundamental shift in how we understand the development of cosmic structure, and it has profound implications for everything that came after, including us. Because our Milky Way galaxy, our home, has a supermassive black hole at its center, and if the pattern from the early universe holds, if our black hole influenced how our galaxy formed, then in a very real sense, we owe our existence to a monster. Without Sagittarius A1, the Milky Way might never have formed the way it did. The gas might have dispersed. The spiral arms might never have appeared. The solar system, Earth, us, we might never have come into existence. I find that thought both terrifying and awe-inspiring. We're here in part because a black hole helped build our home. But we're not done yet. Because as radical as the heavy seed theory is, there's still an even wilder possibility that scientists are seriously considering. What if some black holes didn't form from stars or from collapsing gas clouds? What if some of them were here from the very beginning? In our next part, we're going to talk about primordial black holes, ghosts from the first fraction of a second after the Big Bang. We're going to explore what happens when a black hole acts as the boss of a galaxy, regulating star formation and controlling the evolution of billions of stars. And we're going to tie all of this together to understand what it means for the future of cosmology and our understanding of the universe. But before we move on, I want you to consider this. If heavy seed black holes can form from direct collapse, and if they really did help build the first galaxies, then the early universe was a much more violent, much more explosive place than we ever imagined. It wasn't a slow, gentle process of stars forming one by one. It was a cosmic battlefield where massive structures appeared in violent bursts, where black holes battled with their own radiation pressure, where entire galaxies' worth of gas could collapse in geological instants. And somehow, out of all that chaos, out of all that violence, eventually came stability. Eventually came the calm, organized universe we see today. Eventually came solar systems and planets and life. How did we get from there to here? How did chaos become order? That's the story we're still piecing together, and every new discovery from Webb gives us another clue.
We've established that these impossible black holes exist, and we've explored how they might have formed. But now we need to answer an even bigger question. So what? Why does it matter if black holes were born big or grew fast? What difference does it make to the overall story of the universe? The answer is, it makes all the difference in the world. Because black holes aren't passive objects that just sit in the centers of galaxies doing nothing. They're active participants in cosmic evolution. In many ways, they're the conductors of a galactic symphony, controlling the tempo and volume of star formation, determining the structure and fate of their host galaxies. To understand this, we need to talk about something called cosmic feedback, and it's one of the most important processes in the universe. Let's start with a simple observation. When we look at galaxies throughout the universe, we notice a remarkable relationship. The mass of the central supermassive black hole is almost perfectly correlated with certain properties of the galaxy, particularly the speed at which stars orbit in the outer regions, which tells us about the mass of the galaxy. This relationship is called the m-sigma relation, where m is the black hole mass and sigma is the velocity dispersion of stars. And it's precise, like really precise, to the point where if you tell me how fast the stars in a galaxy are moving, I can predict the mass of the central black hole with remarkable accuracy, even though the black hole itself makes up less than 0.2% of the galaxy's total mass. It's like being able to predict someone's exact weight just by hearing their voice. There's clearly a deep connection there. For a long time, this relationship was mysterious. Why would a tiny black hole in the center be so perfectly linked to properties of stars thousands of light years away? It's not like the black hole's gravity directly affects those distant stars. They're way too far away. The answer is feedback. And it works like this. When a black hole feeds, when it's actively pulling in gas from an accretion disk, it becomes an incredibly efficient energy generator. That infalling material doesn't just fall in quietly. It forms that hot, bright accretion disk we talked about. And in many cases, it launches enormous jets of energy and particles from the black hole's poles. These jets are absolutely mind-blowing in scale. They can expend for millions of light years, far beyond the galaxy itself. They plow through intergalactic space at nearly the speed of light, carrying enormous amounts of energy. Now, here's where it gets interesting. As these jets plow through the galaxy, they slam into clouds of cold gas. That gas is the raw material for making new stars. But when the jets hit it, they heat it up a lot. They can raise the temperature of the gas from tens of degrees above absolute zero to millions of degrees. And here's the critical thing. Hot gas can't collapse to form stars. You need cold, dense gas for gravity to overcome pressure and collapse. If the gas is too hot, the pressure is too high, and gravity can't pull it together. So the black hole, by feeding and producing jets, is essentially turning off star formation in its galaxy. It's blowing a cosmic stop sign that says, no more stars allowed. This creates a self-regulating system. When a galaxy has lots of cold gas, stars form rapidly, and the black hole also has plenty of material to feed on.
As the black hole feeds, it gets more active, produces stronger jets, heats up the gas, and slows down star formation. With less star formation, less gas is processed, so eventually the jets quiet down, the gas cools, and the cycle begins again. It's a feedback loop that keeps galaxies in balance. Without it, galaxies would grow out of control, forming stars until they ran out of gas entirely. With it, galaxies grow at a measured pace, with periods of activity and periods of quiet. This explains the M-sigma relation. The black hole and the galaxy don't just coexist, they co-evolve. They grow together, influencing each other, locked in a cosmic dance. The black hole can't grow too much without affecting the galaxy, and the galaxy can't grow too much without feeding the black hole. But in the early universe, in those first few 100 million years, this relationship was probably very different. Those early overmassive black holes, the ones where the black hole is as heavy as the entire galaxy, represent a situation where the black hole got ahead of the curve. It grew so fast, so early, that the galaxy couldn't keep up. And this might have had profound effects on how those early galaxies evolved. A superactive black hole in a young galaxy would have been suppressing star formation aggressively. These might have been galaxies where, ironically, the presence of a massive black hole prevented most stars from forming. In the modern universe, we see this in what we call red and dead galaxies, massive elliptical galaxies that have stopped forming new stars. They're red because old stars are red, and they're dead because no new stars are being born. And in almost all cases, these galaxies have very massive black holes that likely shut down star formation billions of years ago. But in the early universe, seeing this happen so quickly, with black holes so dominant, would have shaped the entire evolution of structure formation. It might explain why some early galaxies grew so big so fast, while others stayed small. It all depended on how active their central black holes were.
There's another layer to this too. When massive black holes merge, which happens when galaxies collide, they release an enormous amount of energy in the form of gravitational waves. We can now detect these waves using instruments like LIGO for stellar mass black hole mergers, and in the future, space-based detectors like LISA for supermassive black hole mergers. These mergers don't just combine two black holes into one bigger black hole. They're violent events that can send shock waves through both galaxies, triggering bursts of star formation in some regions while heating gas and shutting down star formation in others. They can even kick the merged black hole out of the center of the galaxy if the merger is asymmetrical enough, sending a supermassive black hole careening through space like a cosmic cannonball. So black holes aren't just passively sitting in galactic centers, they're active players. They're managers, regulators, and sometimes destroyers of their host galaxies. And this brings us back to us, to the Milky Way, to Earth. Our galaxy formed around 13 billion years ago, not long after those early monster black holes we've been discussing. Sagittarius A star, our central black hole, has been here from the beginning, growing alongside our galaxy. And at various points in our galaxy's history, it's been active, feeding, producing jets, regulating star formation in others. The spiral arms of the Milky Way, the regions where most stars form, including the region where our sun formed, were shaped in part by the energy output from Sagittarius A star, billions of years ago. The gas that collapsed to form our solar system, the heavy elements that make up Earth, the carbon in our bodies, all of it was influenced by the presence of that black hole. In a very real sense, we are the children of a black hole. Without Sagittarius A star shaping the development of our galaxy, we wouldn't be here. The gas might have collapsed differently, the spiral arms might not have formed where they did, the sun might not have ignited in this particular part of space. I find that thought both humbling and remarkable. We spend so much time thinking of black holes as destroyers, as cosmic monsters, as the ultimate enemy of life. And it's true that if you get too close to one, it will absolutely destroy you. But on cosmic scales, on the scales of galaxies and star formation, black holes aren't destroyers, they're architects. They're the foremen of the construction project that built the universe we live in. And that means understanding them isn't just about satisfying curiosity or solving abstract physics problems. It's about understanding our own origin story. But we're not quite done yet, because there's still one more piece of this puzzle we haven't fully addressed.
We've talked about heavy seeds forming from direct collapse, but there's an even more radical possibility that scientists are seriously investigating. What if some black holes didn't form from stars or gas clouds at all? What if some of them were created in the first fraction of a second of the Big Bang itself? What if some black holes are literally as old as time? In our final part, we're going to explore primordial black holes, the ultimate heavy seeds, ghosts from the birth of the universe. We're going to look at what the future holds for this field of research, what new discoveries we might make, and what all of this means for our understanding of reality. But before we get there, I want you to think about this. If black holes helped build galaxies, and galaxies are where stars form, and stars are where heavy elements are forged, and heavy elements are what planets and life are made of, then in the chain of causation that led to your existence, black holes are one of the first links. You are made of atoms that were forged in stars. Those stars formed in galaxies. Those galaxies were shaped by black holes. In a very literal sense, you are connected to the most extreme objects in the universe. Your existence is a consequence of their existence. That's the kind of thought that makes me stop and just stare at the night sky sometimes. We're part of this incredible, vast, ancient story, and we're only just beginning to understand it. We've covered a lot of ground. We've seen how the old theory of slow black hole growth has fallen apart in the face of new observations. We've explored the idea of heavy seeds forming from direct collapse. We've discussed how black holes act as architects and regulators of galactic evolution. But there's one more theory I want to talk about, and it's the wildest of them all. It's also, in some ways, the most elegant solution to our timeline problem. What if some black holes were created in the first fraction of a second after the Big Bang itself? These would be what scientists call primordial black holes, and they're one of the most fascinating theoretical objects in all of astrophysics. Here's how they might form. In the very first moments after the Big Bang, we're talking about times like 10 to the minus 30th seconds, fractions so small they're hard to even conceptualize. The universe was incredibly dense and hot. It was essentially a seething soup of energy and matter, expanding and cooling rapidly. But it probably wasn't perfectly smooth. There were likely tiny fluctuations in density, little regions where matter was slightly more concentrated than in the surrounding space. These fluctuations would have been microscopic, quantum-scale variations. But here's the thing. When density is high enough, even small variations can be significant. If one of these slightly denser regions was dense enough, and if the conditions were just right, the enormous pressure of the Big Bang itself could have collapsed that region into a black hole. Not a black hole formed from a star's death, not a black hole formed from a collapsing gas cloud, a black hole formed directly from the primordial energy of the universe's birth. These primordial black holes could have a wide range of masses. Some might be tiny, microscopic even, but others could be massive, potentially thousands or even millions times the mass of the Sun. And they would have existed before the first atoms formed, before the first stars ignited, before anything we normally associate with the universe came into being. If these objects exist, they would be the ultimate heavy seeds. They would have been sitting in the darkness, waiting as the universe expanded and cooled around them. And when the first gas started to clump together to form galaxies, these pre-existing black holes would have acted like gravitational magnets, pulling in material and jump-starting the growth of supermassive black holes with a massive head start. This would completely solve the timeline problem. If you start with a black hole that's already a million solar masses the moment the universe allows normal matter to exist, then reaching a billion solar masses in 400 to 500 million years becomes trivial. You're already 99% of the way there. But do primordial black holes actually exist? That's the billion-dollar question, and honestly, we don't know. They're theoretically possible based on our understanding of physics, but we've never definitively detected one. However, there's been a lot of excitement in recent years because primordial black holes could potentially solve multiple cosmic mysteries at once. For one thing, they're a candidate for dark matter, the mysterious invisible mass that makes up most of the matter in the universe. If a significant fraction of dark matter is actually primordial black holes, that would be a stunning discovery. And now, with the observations from James Webb showing these impossibly early supermassive black holes, primordial black holes as seeds have become a much more serious possibility. Some recent papers have proposed that a combination of primordial black hole seeds plus rapid accretion could explain what we're seeing. The beauty of this theory is that it pushes the mystery back to the very beginning. Instead of asking, how did black holes grow so fast, we're asking what were the conditions in the first moments of the Big Bang that allowed these objects to form. It connects the smallest scales of quantum physics to the largest scales of cosmic structure. It unifies the very beginning of the universe with the galaxies we see today. Whether primordial black holes turn out to be the answer or not, one thing is clear: we are living through a golden age of cosmological discovery. For thousands of years, humans looked up at the night sky and wondered about the nature of the universe. For thousands of years, we could only speculate, creating myths and philosophies to explain what we saw. But now, for the first time in human history, we have the tools to actually find out. James Webb is just the beginning. In the coming years and decades, we'll have even more powerful telescopes, both in space and on the ground. The giant Magellan telescope, the extremely large telescope, and eventually telescopes in space that will make even Webb look small. We'll map the early universe in unprecedented detail. We'll watch black holes being born. We'll see galaxies forming in real time, or at least in their distant past that we're observing now. We'll measure the growth rates of black holes, track how galaxies evolve, and piece together the full story of how the universe went from a hot, dense, nearly uniform soup to the rich, structured cosmos we see today. And every new discovery has the potential to overturn what we think we know. That's the nature of science. We build theories based on the best available evidence, and then when new evidence comes in, we revise those theories. We're never done understanding the universe because the universe keeps surprising us. These supermassive black holes in the early universe are the latest surprise, but they won't be the last. I started this journey by comparing early black holes to an impossibly large tree growing in freshly formed soil. That analogy still holds, but now we understand more about why the tree seems impossible. We know about the Eddington limit, the speed limit for growth. We know about the seed mass problem. Starting small makes reaching massive sizes nearly impossible in the available time. And we're discovering potential solutions: heavy seeds from direct collapse, super Eddington feeding, and possibly even primordial black holes from the Big Bang itself. But beyond the specific scientific questions, there's something deeper here, something that goes to the heart of why we do science at all.
We live in a universe that is vast beyond comprehension. The observable universe contains something like 200 billion galaxies, each with hundreds of billions of stars. The scale is so enormous that our brains can't really grasp it. We can say the numbers, but we can't truly feel what they mean. And yet, despite that vastness, despite the fact that we are unimaginably small and short-lived in cosmic terms, we can understand this universe. We can point our telescopes at the edge of the observable cosmos, capture light that has been traveling for 13 billion years, and decode the messages hidden in that light. We can figure out the physics, work out the math, and understand what's happening. That's extraordinary. That's almost miraculous. A species that only developed agriculture 10,000 years ago, that only figured out the Earth goes around the sun 400 years ago, that only built computers in the last century, is now unraveling the birth of the universe itself. And we're doing it not because we have to, not because there's any immediate practical application, though often there are unexpected practical benefits from fundamental research, but because we're curious. Because we want to know, because something deep in the human spirit looks at the unknown and says, I want to understand that. The mystery of the early supermassive black holes is just the latest chapter in that never-ending story of discovery. And it's a chapter that's still being written.
Right now, as you're reading this, James Webb is out there collecting data. Astronomers are analyzing it. Papers are being written, debated, revised. New theories are being proposed. New observations are being planned. We don't know yet how this mystery will be fully resolved. Maybe it's direct collapse black holes. Maybe it's primordial black holes. Maybe it's super Eddington accretion that we don't fully understand yet. Maybe it's some combination of all of these. Or maybe it's something completely different that no one has thought of yet. But we're going to find out. That's the promise of science. The questions might be hard, the answers might be slow in coming, but eventually, through observation and experimentation and careful reasoning, we figure it out. And when we do finally understand how these girly black holes formed and grew, we'll know more than just an interesting fact about astrophysics. We'll understand something fundamental about how structure emerged in the universe, how order arose from chaos, how the dense, hot, uniform soup of the Big Bang transformed into galaxies and stars and planets, and, eventually, us. Because that's what this is really about. It's not just about black holes. It's about the story of the universe, which is also the story of us. We are part of this cosmic tapestry. We are made of atoms forged in stars, living on a planet orbiting a star, in a galaxy shaped by a black hole, in a universe that somehow went from nothing to everything in the span of 13.8 billion years. Understanding how black holes grew so fast in the early universe is understanding one crucial chapter in that story. And like any good story, it's full of mysteries, surprises, plot twists, and moments that make you sit back and say, wow, I did not see that coming. So, here's where we are. We know these impossibly early, impossibly massive black holes exist. We have multiple competing theories for how they formed. We have more data coming in every day, and we're closer than ever to finally solving one of the biggest mysteries in the history of cosmology. To everyone who has stuck with me through this entire journey, thank you. I know we covered a lot of complex physics, a lot of big numbers, a lot of abstract concepts, but I hope you're walking away with a sense of just how incredible this moment in scientific history is. We are witnesses to the universe revealing its secrets. We are the generation that gets to see the cosmic dawn, the birth of the first galaxies, the formation of structures that would eventually lead to everything we see around us. We get to watch as scientists around the world work together to solve mysteries that seemed completely impossible just a few years ago. And we get to know, really know, with evidence and data, not just speculation, more about the universe than any previous generation of humans ever dreamed of knowing. That's a privilege. That's an honor. And it's a reminder that for all our problems and challenges as a species, we're also capable of remarkable things. We can build telescopes that see across billions of light years. We can do math that describes the behavior of black holes. We can work together across national boundaries and cultural differences to expand the frontiers of human knowledge. The impossible black holes in the early universe aren't just a scientific puzzle. They're a reminder that the universe is bigger, stranger, and more wonderful than we imagined. And they're an invitation to keep looking, keep questioning, keep discovering. Because the universe has more secrets, many more. And every time we solve one mystery, we find 3 new ones waiting behind it. That's the beauty of it. The adventure never ends. The story keeps unfolding, and we get to be part of it. So, the next time you look up at the night sky, remember, some of those points of light are galaxies billions of light years away. Inside those galaxies are black holes that formed when the universe was young, black holes that helped build the cosmic structures we see today, black holes that are still whispering their secrets to us across the void. And we're listening, and we're learning, and slowly, piece by piece, we're figuring it out. The impossible is becoming possible. The unknown is becoming known, and the universe is revealing itself to us in all its magnificent, mind-bending glory. What a time to be alive.